Hi, I'm Zeynep.
Yeah, me, it's Nicolaj. We present today the project Morphology of Sound, which was founded by INTRA, which is a research fund at the University of Applied Arts. And we combine two departments, the Department of Architecture and the Department of Digital Art, together in this research project. And as it is written here, it's an exploration of bilinearal feedback between architecture and sound, which is conducted by artificial intelligence, by KI.
Exactly.
You want to add something to that?
Yeah, actually we met through the project. Funnily, I thought Nico was actually only a sound artist or a digital artist, where I then found out that he's an architect too. I'm an architect. I don't have anything to do with sound, so I'm sorry if I use wrong terminologies. Yeah, now I give you the word.
Okay, our starting topic was the combination of sound and architecture, or sound and space, as a research topic. And this has already a very long tradition, and everybody who get known about this project immediately knows what it is about, without that the relationship between sound and architecture having been specified. This is done with an idea of architectural and sonic elements that are assumed in the discussion without discussing them further. And our approach was to take a closer look at these different approaches and ideas about these elements, what they are and how they can be combined in order to clarify our research approach. So acoustic itself, the slides are in German. Acoustic is always mentioned first when we talk about sound and architecture. And that's because room acoustic is already discussed by Vitruv, which was one of the first architectural theories. In his fifth book, he describes the placement of vessels to improve speech intelligibility. What happens here, it is a physical object, and their properties change the acoustic of the room. Wallace Sabina, between 1910 and 1950, developed a formula named after him for calculating this reverberation time. And during this scientific research into room acoustic, it became clear that absorption coefficients and the diffraction behavior of physical objects, again from physical objects, structure the room through acoustic possibilities. However, practical acoustics, how it is applied in architecture, only describes the properties of physical objects that lead to at least a single acoustic characteristic value of a space, and not to the differentiated structuring of the room through hearable elements. Research into binaural hearing is far less well known. It was Venturi who carried out the first attempts to research directional hearing in the late 18th century. However, it was not until the middle of the 19th century that research into binaural hearing was taken up by the scientific community. Despite Venturi's clear results, the subject was ignored for 50 years. It was not until the end of the 19th century, around 100 years after Venturi's research, that hearing was scientifically accepted as a space-perceiving sense. In this context, however, spatial perception means directional perception. The result of directional hearing lead to the listening devices of the First World War, which one of them is seen in the picture. These two fields of research, the room acoustic and the binaural hearing, were developed independently of each other, and it was only in the medium of the radio, which began to establish itself from around 1920, that they were combined to form what is known as acoustic space. Acoustic space means in this, it's always individual perceived sound, and space is somehow sonified in this sound. So it's so we come to the next point, the spectromorphological space. Hermann Helmholtz imagined this individual perceived around 1815 as a tonal space, and by this he meant the same space but with a chromatic grid as Pierre Schaeffer in Musik Konkret around 100 years later. Helmholtz places the pitches of the tonal spaces depending on the scales used in the music. Schaeffer places the noise, so the sound of the everyday or the urban sounds, places this noise, which were also used in the Musik Konkret, and calls it the sound object, the objet sonore. He explains the properties of this object with the morphology of the spectral representation. That's why it's called the spectromorphological space. And this space has the axis of volume, frequency, and time, so it has nothing in common with the architectural space, which has the axis x, y, z, but represents a further association with the theme of sound and space. The third association with sound of space, which always comes in mind when we talk about this project, is the structural equivalence between sound or music and architecture, which emerged as a kind of topic in the 19th century and lead to the idea of the Gesamtkunstwerk and was described by Arthur Schopenhauer with the sentence, "Architecture is frozen music." It is most prominently represented in the 20th century by the work of Yannis Xenakis. The idea is that both architecture and sounds are transformed into a kind of mathematical space in order to pretend that they have a common origin. This structural equivalence suits architecture as Leon Alberti in the Renaissance has already introduced a dichotomy that distinguishes between plans, in other words, a geometrical based representation, and it should not be forgotten that geometry was a subfield of mathematics until the 18th century, so it's a kind of mathematical space, this plan, and architecture. And thus also between the so-called voyeur and the pédestrian, the Fußgänger, as Michel de Certeau calls it, that is a mathematical external point of view on architecture and a phenomenological internal point of view on architecture. While Certeau emphasizes this difference as a juxtaposition in Alberti's concept, so in the architectural concept, this is already to be understood as a unity. The 2 points of view are connected by a third element, the projections, the depictive, the psychological, and the cybernetic projection. The advantage of this medial construction, how I would call it, of architecture lies firstly in the possibility of distributing architecture. On the other hand, it has enabled a development of design methods that are only possible in this mathematical space. But what does this all mean for the sound? As we have seen, there are 3 positions which are always in mind when we talk about this combination. It is either viewed as a property of physical objects, or as an individual perception, or as part of abstract mathematics. These are always considerations that are favorable for architecture, in which sound is considered from the point of view of architecture. It is architecture that primarily negotiates physical objects in architectural space and shifts everything else into the realm of individual perception or abstract spaces. So we wanted to start from a different kind of point when we combine those 2 science fields. With the emergence of sound art, which developed from around 1915, sound established itself in the practice of fine art as an entity in space, as an element that organizes architectural space, that is the space August Schmasow is referring to, the architectural space. Initially, this approach had no vocabulary, no ontological basis to describe sound art in terms of material, as Christoph Cox notes. But at the latest, since Casey O'Callaghan developed a sound ontology in 2010, on the basis of which sound can be thought as an independent entity in space. This has changed for sound. But now we have to ask the other way around, what does this mean for architecture? For architecture, it means that there are elements in space, new elements in space for the architectural thinking that are time-based, that is events that structure the architectural space as elements of the architectural space and can therefore be designed architecturally. However, architecture always falls back on an ontology that describes the world as consisting of physical objects that are medium-sized, such as apples or skyscrapers, and that are made of solid matter that can be touched or seen. In this architectural ontology, there are no time-based events that cannot be touched or seen, like sound. If you want to think architecture in terms of sound and not think about sound within architecture, you have to rethink this architectural ontology. Henri Lefebvre's rhythm analysis from 1992 provides a corresponding approach in which he begins to question precisely the timelessness of the thing. But if all elements of space are events, then the reception of space itself is also an event. So we have to think about the perception itself as well. If I only hear sound and concentrate on listening in a monosensory way, and perhaps even try to stand still, there's a kind of isonorm that says when you do sound walks, you have to stand still and look in a certain kind of direction. If you do this, so it's somehow stands behind this the idea of the city as a large composition, as Murray Schaffer defined as the basis of his research. Then I only hear the sound in the spectromorphological space. It's a question of perception. I do not change the ontological basis of architecture. I musicalize the architectural space by continuing the reception behavior of listening to music that developed in the concert system of the 19th century. If I want to think architecture in terms of sound, and this should be the starting point of this research project, I have to perceive the audible elements in architectural space as architectural elements on an equal footing. I have to interact with architectural space by listening. Nochmal zum anderen zurück. And what does this mean, this interaction with space? It started while the futurists were still celebrating movement without actually carrying it out in architectural space. The Dadaists went on excursions and regarded movement itself, that is interaction with space, as artistic material. This subsequently led to the situationists' concept of psychogeographical space. They organized space through different atmospheres and thus established the concept of psychogeographical urbanism, which they understood as manifesting itself in music. This movement, specifically walking as an exploration of everyday space and so of everyday sound, also lead to a list of sound effects found at the Institut Cranson in France, which organize architectural space, but which can only be perceived through interaction with space. So these sound effects are, beneath the event of the sound itself, a kind of element of architectural space, which only can be perceived by walking through it or interacting with it by listening. So the conclusion of all this, which gives us a kind of ground for our artistic research project, thinking of architecture through sound thus leads to a series of new spatial, acoustically perceptible elements, new for architecture of course, and events that structure architectural space, and to the conclusion that the physical object itself, so the original architectural object, can also only be understood in their temporality, and that this can only be perceived and experienced through interaction with space, which is in itself an event, the interaction. So if Schopenhauer's sentence could be a kind of definition of our research project, we have to reverse it, and it should be called sound is defrosted architecture. But let's think back, we also established a kind of medial construction of architecture, which consists of the external point of view, the voyeur, and the internal point of view, the Fußgänger, and three kinds of projections, the depictive, the psychological, and the kybernetische projection should also be understood as an event within this project. So the realization of this event is carried out in real time, or we try to carry out it in real time using an artificial intelligence tool, which Zeynep is now talking about.
So yeah, Thank you. So basically, our project is highly inspired or highly influenced by cybernetics, and we focus mainly on this idea of interaction and communication, and how do we interact with non-human artificial elements in our space, which are actually architectural objects. So in this case, we are trying to find a language between the voyeur, perceptor, or visitor, or human, and the architectural object, which is not necessarily human language. So our main inspiration comes from the work of Gordon Pask. I don't know if you know him. He's a cybernetician, and he has, back in the 60s, he built this machine called music color machine. So he was looking into, he was actually a programmer, but he was teaching in architectural schools, and he was looking into how communication routines can be implemented between humans and machines to give rise to a new language of emergent art. So in this case, for example, in the music color machine, there's a composer inputs music, kind of a composition, playing piano, and the machine outputs some kind of a light. And the composer is trying to control this light output while the machine is learning from the changing composition and changing also its light output. So by this interaction between the machine and the composer, a new kind of a musical composition and light composition emerges, which is not necessarily controlled by the composer themselves or by the machine itself. So we are definitely looking into this intersection, so how two completely different species can influence each other and communicate with each other. So I'm not going to talk very deeply into cybernetics, but AI is a part of cybernetics, and we use AI to actually control the behaviors of these architectural objects that we will be talking about. Short about AI, obviously there is a lot of myths about AI and how it's going to take our society, take over our society. If you have been Googling OpenAI once, you have definitely a Google feed about AI conquering the world in the next 2 years, if you use Google, obviously. But don't be afraid, it's only maths. So if you have been working with mathematics, it's just a complex combination of very simple mathematical rules and functions that are able to learn certain strategies. What we use is reinforcement learning. So it is actually, our architectural objects are, we can see them as small little robots who explore their job, their task, which I will be talking about shortly, by trial and error. So these kind of strategies are used actually in your, I don't know if you have a robot Hoover. So by hitting the walls, the Hoover learns to not to hit the walls. So this is exactly what we are doing. It's not very complicated. So basically, we have a front end and a back end. So in front end, we have an external impulse that we are getting from an external agent. This can be movement or an incoming sound. This is movement in our case, or an incoming sound. And there's this decision-making tool controlled by a pre-trained reinforcement learning algorithm that kind of controls the behavior of our objects. And through this outputted behavior in these two objects that we will be showing, one of them is actually shaking and vibrating, and the other one is outputting sounds. The external agents start to communicate with these objects. Just to keep in mind, we are not trying to mimic or produce any sound. We explore actually intrinsic physical properties of these objects. In this case, this is we call it a bush. This was developed by our students at the Technical University, and they were exploring this kind of reciprocal, not static structures. So what if actually, if everything vibrates, what if we start designing vibrating structures? And they were basically calculating the vibrations in order to induce more vibrations to the structures for them to be able to actually vibrate in their initial frequencies, and then by amplifying these frequencies, you could go on and listen to the sound at the end of each stick. So this is a small video. This project, I have to admit, you will see his name at the end, but wouldn't be possible without the input of Klaus Philipp, who is sitting at the end. Now we don't have sound. So, as you see, we were exploring actually the idea of architectural elements in our teaching, in our interdisciplinary teaching. Actually, we were bringing the digital art students with the technical university students. I teach structural design at Technical University, so it is like completely two different groups of people coming together and interestingly building a very interdisciplinary group where, you know, some of them were also very interested in sound design.
Yeah, but as we explained before, it was always the task that you include a kind of audible or hearable structure in your design project, which can be perceived by walking around it. In the example of the sticks, it's always hearable at the end of the sticks. Depending on the stiffness of the whole project, you have different kind of vibrating sticks, and they produce different kind of sounds in the area around the object. So these hearable spatial areas with different kind of qualities was always included in the architectural thinking, but still it was a kind of architectural thinking. They were talking about structures and all the stuff you do when you design architectural project, because this differentiates to normal sound art projects where it's only the sound, the element, where it's the sound, with the sound you try to make spaces, but here you're still in an architectural field, but the ontology of architectural was includes sound-able or hearable elements. We have to say these are two examples of students that were made last semester. It's a still ongoing project, so we design projects on ourselves, which we don't present now because they're not finished yet. Yes, there's another movie of this.
Yeah, I think so. Yeah, it is just 3 slides maybe. I think we would like to finish this and then we can. So basically this project approaches the sound generation from a different way of actuation. We actually use piezoelectric sensors and transducers in order to create a feedback that tries to mimic, and where the system tries to learn to mimic its environmental sounds. So there are 2 steps actually. So there's a training process where the system is kind of listening to its environment and trying to turn on and off different piezos in order to create different sounds. And on the other hand, if it was able to, after the training, it basically starts to react to its environment by outputting these sounds. The interesting part in this is actually in regard to wherever we locate the piezos, we can generate different feedbacks because the stiffness of the structure changes due to this folded shape, where different folding angles, different sizes, different locations in the structure also have different vibrational properties. Yeah, so maybe you want to summarize? Yes. So in summary, basically, yeah, we are looking into the interdisciplinary thinking between sound and architecture, and thank you very much.